This conference will now be recorded.
Third time lucky. Right, history of the structure, the existing structure itself, development and the investigations into it, the current solution, delivery as it is on site at the moment, and then a closing summary. So before I dive into that presentation though, the bridge or the structure forms part of the East-West Rail programme, which is obviously to connect Oxford and Cambridge, as you'll be all aware. The programme falls into three phases. Phase 1's complete. This is a part of phase 2 that effectively connects Bicester to Bletchley. The phase has been delivered by the East-West Rail Alliance, which is 4 parties. One is Network Rail, one is Laing O'Rourke, Volker Rail, and Atkins, that are effectively put into a combined team with a charter and a set of behaviours about how they operate to try and make it a single team to deliver the scope of works as efficiently and as effectively as possible. Scope, as you can see, the line between Bicester and Bletchley onto Milton Keynes, a lot of that is a mothball railway that's now being being brought back into use. There's a significant amount of earthworks you can see from the right-hand side of circa 1 million tonnes, or sorry, cubic metres, 100 kilometres of track, a whole heap of bridge works, and obviously the new railway signalling communication systems and the structure itself, BFO. So a bit of history. BFO, NEC 152A, was built between 1958 and 1960. It connected the OXD line to the Bletchley-Bedford-Midland line, BBM. It provides the grade separation of the West Coast Main Line, and despite being finished in only the early 60s, it was closed to passenger services by 1968 due to the beaching report and the activity that followed that. It has, however, been used for heavy freight for quite some time until very recently, and the first few years of its operation it was used quite heavily with a couple of iron ore trains most days travelling over the structure. It then got used for aggregates for about 20-25 years for the construction of Milton Keynes, and has subsequently been used almost as a stabling yard for freight trains looking for paths onto the west coast. So it has seen some service, although it is limited and not as originally intended. So the existing flyover, it's 605 metres long. It consists of 37 spans. It not only crosses the West Coast Main Line, but also crosses 2 major roads, Water-Eaton Road and Buckingham Road. It is made up of a mix of structural elements, both pre and post-tension pre-stressed concrete. And I will go through those in a little bit more as we go through the presentation, because they are quite significant to the selected works. It also has a lot of reinforced concrete elements, just plain reinforced rather than pre-stressed. And the one thing to take away from the structure is it's not a structure, it's actually 4 different structures, which are very different in how they are, how they were built and how they perform. So let's go to the structure type 1. Structure type 1 is what's called the northern spans, although it isn't just the northern spans. It's span 12 to 16 and 32 to 37. And you can see a kind of a long section of the bridge on the viaduct on the bottom of the slide, with the different types of structure marked. And on the picture, I will just call up where the 2 areas where there are northern spans. These are pre-stressed, pre-tension beams, effectively made in a factory. And those are the green beams you can see at the underneath the deck. a reinforced concrete deck is cast on top of them, and those are supported on reinforced concrete piers, which are again supported on either reinforced concrete piles or pad foundations, depending on the geology. Nice and simple and straightforward. There's just a drawing of the pre-stressed beams themselves, and if you look to the right-hand side of the screen, there's a cross-section through the beam, and all those little crosses are effectively stressing strands that are pulled tight. The concrete is cast around them, and when it's gone off and reached sufficient strength, those are cut, and that puts a pre-stress in the beam, hence the description, and that increases its capacity to support loads. Next up, we have the West Coast mainline spans. Over the West Coast, unsurprisingly. These have a similar deck in terms of its, again, pre-stressed, pre-tension beam supporting a cast in situ concrete deck. But these are supported on half joints at each end. And again, we'll have a look at half joints when we get to that part. But it's on alternating portal piers and crossheads and T-piers. And this enables it to kind of almost tiptoe across the railway and allow the railway to go through it in a very ingenious and clever arrangement. And here's a photo of it being erected. You can see the portal pier there, and the crosshead with the two gentlemen standing on top of it. No safety harnesses, no helmets, so don't make the safety guide near the photo. And you can see the crane starting to lift one of those PC beams into place. So, thirdly, we have the Buckingham Road spans. These are different yet again in terms of their construction type. They are a mixture of reinforced concrete and post-tensioned pre-stressed concrete beams sitting on post-tensioned pre-stressed piers. To try and explain this a little bit better, what you see in the colours below for the bridge, the yellow parts are just reinforced concrete cantilever structures with a backspan. You then have the infill or suspended spans in orange, and the orange are pre-stressed beams that are post-tensioned, then lifted into place, and a reinforced concrete slab placed on top of them. The indigo or the blue parts are pre-stressed but post-tensioned concretes. They effectively consist of lots of, within them have lots of bars that are in ducts that are then tightened up and meant to be grouted to lock the stress into the structure so it can continue to perform. And here is another view of another crane and the construction site you can see, and the operating railway in the background. So, as I mentioned earlier, it was built in 2 phases, and here, a bit of detective work was required here. When you see that this photo has an abutment on it, and you can see the northern spans, or one part of the northern span, stretching off into the distance. So you're effectively looking east. But why is there an abutment in the middle of nowhere? And why does this abutment now make up Pier 11 on the structure as a whole? Well, what we've managed to find out was that when they were building this section, they were building an embankment, and they had a number of structural failures where the embankment collapsed. There was effectively a disused track, or there is a track bed at the bottom that follows the alignment of the viaduct, and that there was a derailment due to the track slip. So, particularly with the level of water in the vicinity and the height of the embankment, they obviously decided that it was better to build structure through here rather than the embankment that they previously proposed. And so we have what are called the southern spans, which are now marked 1 to 11 and coloured in there. And these just happen to be a different form of structure yet again. These are, it's a cast in situ deck. It's a voided slab, hence the holes you can see there. It has ducts that are put into those that slab. And I think we can see some of those ducts on this cross section here between the voids that again actually have post-tensioning bars put in them there, and then they're tensioned. So again, we have a pre-stressed piece of concrete which enhances its capacity to be reinforced, and it's post-tensioned because they were installed after the concrete had reached strength. So that's the structure. And as you can see, it is many and varied and quite complicated. So the early development works and investigations that were done. One of the main elements of the work that were in the original scheme was replacing all the bearings. There was a number of inspections, and they look in particular, some of them look in particularly poor condition, and therefore there was a recommendation whilst the railway was available and before the East-West Rail services were operated over it, would be worth replacing them with modern equivalents. There were also a number of failures to reach the RA10 capacity at 40 miles an hour without strengthening, and this falls into a number of areas, the largest being which the piers. Nearly all the piers failed under traction and braking loads, and what we've discovered is effectively the application of traction and braking loads from BS 153 through to the current code. They've almost doubled. So effectively, the change in the code has caused these to become failures, and it's very unusual with structures of this sort of size that would be a problem, but fundamentally when you put the numbers to it, none of the piers stand up. Also, there are some half joints, and I'll keep talking about half joints as we go through this conversation, particularly the ones on the crossheads over the West Coast spans were only able to demonstrate RA5 capacity. And some of the half joints, particularly the West Coast ones, were showing appear to be in poor condition. And we've got a crosshead there to our right. You can see the half joints, which are really helpful in allowing you to reduce the construction depth of the span when you're putting elements together. But when you actually dig into the detail of it, when you look at these ones on site, you can see that there's been a number of repairs with resin injection, and that second crack is rather ominous in terms of its shear. Looks like it's a shear crack where you would expect the beams to fail. I will cover these a little bit later, but they were found generally to be restricted to the ends of the beam rather than in the centre. But one of the key challenges with these half joints is you can't inspect them, so you don't know whether that is just at the very edge of the structure, or is a much deeper, a much more significant defect. And the reason half joints are such an issue is explained by bridge failure in Lecco in 2016. Worth googling it and having a look at the videos. But fundamentally, in Lecco, it was an abnormal load that had been given clearance to go over the structure. As it crossed the structure, it failed. And the reason for showing this is I don't know whether the joint was in poor condition or the load should never have been allowed on the bridge. But the point is, you don't get warning about the failure. It is a sudden brittle type failure rather than giving you something progressive or ductile. So again, when you're trying to maintain and manage it, you don't know when it's going to, or if it's going to fail. So the scheme that was being developed at this time consists of strengthening all the substructure components, as you can see the red on the portal piers, replacing the crossheads, the yellow piece you can see there, and refurbishing the decks, making sure they were good order. And this was to be done by using a gantry crane that moved up and down the structure. And then in the autumn of 2018, there was another collapse in Italy. Italy's not getting a good press with my presentations here. It's called the Miranda Bridge. in Genoa. And this left a lot of bridge owners soul searching, should we say, to understand how they could manage their assets better to prevent these types of failure. Again, I don't know the full detail, and I don't think the reports are out yet, but it makes you think about elements of the bridge you can't see that can cause it to fail in an unpredictable or sudden manner. So the level of post-tensioning special investigations, sorry, another acronym, were increased. There was specific scrutiny around hidden critical elements within the structure, and a BD 5415 assessment. It comes from the highways environment, but is a way of helping bridge owners and asset managers prioritise their the work and inspections to their structures. So what actually happened when we got to that point? Well, we found that 90% of the vertical and inclined tendons, particularly in the piers, were ungrouted. So here's a picture from an endoscope that shows the duct, the outside of the duct, and shows the bar in the centre and generally quite good nick, but shows no grout. Conversely, we found about 10% of the vertical and inclined tendons contained grout near their bases. They weren't fully grouted, but they actually had some grout, which made it difficult to grout, if that makes sense. And 10%, a different 10% approximately, of the post-tensioning ducts contained water. So we had the post-tensioning bars in ducts where it would be difficult to grout them standing in water. And there had been some evidence of corrosion at the bottom of the duct. So here's a cross section through a pile cap. You can see the piles on the bottom, and what you see there is a stressing pit in yellow and some grouting tubes in green. So again, looking at it through 90 degrees, you can see the stressing pit. You can see the bars coming vertically into it. And the idea was that you actually filled up the stressing pit once you've done all the works, and you sealed it by grouting through the green tubes, which was ineffective. So what we found when we broke it all out is that we had a pocket where that green triangle is, which on one of the two piers we exposed was full of water. Okay, so as part of this exercise, we did some vacuum tests to see whether we could find effective ways of grouting the ducts, and this proved to be variable. So again, our methodology for grouting the bars to protect them and allow them to continue in service was challenged. And finally, we did an assessment, or we did some pull-off tests to understand the variability of the post-tensioning that had been retained within the bars on the structure. And of the 6 tested, 2 has significantly less pre-tension or preload than expected, which meant that the strengthening we were proposing would need to be further enhanced. And one of them was as low as 25%. So again, with a limited sample, we had an indication that there was quite a lot of variability in the structure that, again, we would need to find a way of validating. So all of those features are effectively contained or constrained to the Buckingham Road and the West Coast spans. And when we did the BE 54 assessment, this was kind of borne out again in terms of the risk rating for the various spans. The southern and northern spans are fairly low at 50-odd%, whereas the Buckingham Road and the West Coast spans were almost 80%. And this isn't an absolute number. What it does, again, as I was saying, is it allows the bridge owner to prioritise interventions and inspection work. One positive from the additional investigation was that when we looked at the rockers and the rollers, the bearings that are there, although there are signs of significant corrosion, once you actually went in there and cleaned it off and inspected the bearings themselves, you were talking about, although lamination's up to 12 mil, you were looking at reductions in thickness of between 1 and 2 mil at max. And the bearings underneath were generally structurally sound on the northern and southern spans. Later on, we were able to demonstrate that the bearings actually did move sufficiently to enable the decks to breathe under thermal load changes. So they were actually doing their job, even if they look rather horrid from the photos. So the challenge we have is related to the west coast of the Buckingham Road spans. We're sitting there with a scheme with continual discovery about the condition and the complexity of the structure from the 1960s. We had difficulty demonstrating to the RAM, or to ourselves, that the capacity and the condition of vertical PT, and therefore there was a risk that we would be necessary to expose a very significant portion of it, replace it, or particularly the vertical PT. And this obviously had an impact with associated escalating costs and program and risk for the Alliance. And this was a particular issue for us because the structure is at the eastern end of the works and was critical in the program to releasing all the track works and the systems works into the corridor, because at the other end we were constrained by handover dates with High Speed 2 and Calvert. So effectively the site was locked, rail locked, without actually getting the structure done. So it was a kind of a significant importance to the overall program of the works. So what happened? We started to look for alternatives, and in parallel with some of the works on the towards the end of them, we started looking at options that removed the vertical PT, allowed us to abandon it, removed all the half joints, removed piers where they were vulnerable to vehicle impact, and minimized the strengthening and works to the northern and southern spans to attempt to constrain the scope. So what does the scheme look like? We were effectively reconstructing the whole of the West Coast span, 17 to 25. We're redecking most of the Buckingham Road spans, 26 to 31, and strengthening the substructure, although we have ended up replacing a couple of the piers. And effectively, we ended up doing very little to the retained spans, the other ones, which is limited to effectively waterproofing, drainage, new handrailing, and minimal strengthening to achieve the R810 capacity. I'll explain how we achieve that in a little bit. So that's what the structure looks like, CGI image, large box type structure over the west coast, with the tracks traversing it from corner to corner. It consists of pre-stressed concrete Y-beams with an integral reinforced concrete slab, and it is supported on reinforced concrete piles, pile caps, and shell abutments. So a cross-section of the West Coast span to give you an idea of the geometrical challenges we faced. Firstly, we needed to provide a headroom that enables us to get a TSI compliant overhead line equipment arrangement in place. So we were limited to 5.13 to achieve that, working very closely with the OLE guys to work out how we could get that to function. We needed, to actually have the productivity and to construct the structure safely, we needed at least 3 meters or 3.1 meters from the face of the pier or the pile cap to the running edge, so that we could work adjacent line open. We couldn't lift the track more than a very insignificant amount due to not wanting to increase the load on the retained spans where we weren't working, and also the design for the Bletchley High Level station had been completed. And we would have started to undo the design for the station if we had gone through a lifting scheme. So this kind of boxed us in. So we had a 25-metre span, and we had a construction deck from top of deck to underside of deck, soffit of deck, of just 1.2 metres. So a very slender deck for a railway bridge. And this only works because of, obviously, it's a very wide deck, and the way the load is applied to it, the track going diagonally across, spreads the load over that structure, and enables it to us to get away with a much smaller and thinner deck. Buckingham Road spans 26 to 31. Effectively, we are replacing those decks, those pre-stressed post-tension decks with half joints, with simple Y beams, again, pre-stressed concrete, but these are pre-stressed rather than post-tensioned. Sorry, I made a mistake. The ones that are there at the moment are post-tensioned, or were there. And just a cross-section through to give you an idea. Simple beams, made in a factory, all the strands encapsulated in concrete, very robust, with a reinforced concrete slab cast on the top to compositely. The existing piers were retained. All that vertical post-tensioning in them was removed or decommissioned, and they were grouted up, and we strengthened them externally where necessary. We did have two piers which we had to replace, 26 and 30, and those were so that we could move the traction and braking load around the structure or restrain it in certain locations, so that we could save the existing piers, because we did not want to take out the big piers around Buckingham Road due to the proximity of the road and the size and complexity of the piers themselves. So that's what the structure will look like over Buckingham Road when it's complete. And we then go to the northern and southern spans, where effectively everything above the red line was in scope, and everything below was passed back to the RAM to undertake any repairs, look after the bearings, etc. So just to give you another view of it, effectively, the blue spans effectively kept with a waterproofing and handrailing and drainage scheme. Red spans totally reconstructed. Gold spans generally the redecking with limited works to the substructures where possible. So what do we have to do to get us on this journey? Innovation by design. So first, let's do some lessons. We've touched on a couple of them, but it's worth just reiterating them, I think. First is lessons from Esched in Germany in the late 90s, where an ICE train derailed due to, I think it was a cracked wheel and a set of points. It took out a pier of a bridge, and in the ensuing carnage, effectively 100 people died and a further 100 were injured when the bridge collapsed and the train went into the collapsed bridge. Our situation on, although it's an extremely unlikely event, it still had an extremely high impact. And when you looked at the structure at Bletchley Flyover, all those piers have exactly the same potential, and therefore removing them as part of our design was really key. We have the LECO half joint failure, removing those half joints, making sure the RAM has a good understanding of what he's got and that can maintain, it's a maintainable feature. And removal of hidden critical elements, particularly those who have potential for effectively catastrophic failure. So removal of vulnerable piers, removal of hidden critical elements, and then we go on to the other aspects of our design and safe by design. We have maximised the use of design for manufacture and assembly, which means precasting significant elements. We have gone to great lengths to demonstrate that we can use CWR on the structure, removing joints and other discontinuities, which gave us the added benefit of being able to save our substructures, or the substructure strengthening. And the structure was designed to be an integral part or fit integrally within the railway, as I've discussed earlier. So DFMA, what is DFMA? It's shell units, abutments, sills, beams and parapets. So these are the shell units being, let's go back one, sorry. You can see that there's a pile cap there with cages being, starter cages coming out the top of it. And the shell units are effectively Lego blocks, for want of a better description, that get popped over the top, stacked up, and then a cage popped in the top, and they're concreted up. So you need no false work, and they can be done in close proximity to the tracks. We also have the beams and parapets. So that's a completed shell abutment or wall. Those are all our precast beams sitting there before our recent possession. And there's some sill units with the elastomeric bearings that the beams will land on. So effectively all these bits are just bolted together, not bolted together, doweled together or locked together to form the structure. So a demonstration that we could use CWR, this was a big issue for us in that the codes that are out there at the moment restrict the use of track bridge interaction, not track bed investigation, by the way, track bridge interaction, to curves of 1,500 meters and above. Here on the viaduct, we were down to between 300 and 400 meters. And therefore, we had to go back to the theory and the understanding that made up the code so that we could demonstrate that come up with one, actually the value of what stress we could put in the tracks, and two, residual stress allowance, should I say, because the tracks obviously, or rail takes a whole series of stresses from the vertical loading to its performance as a stressed element within the CWR system. But there's an allowance within the track that you can utilise for to prevent buckling, and the work by Meyer in Germany in 1937 provides the basis of that. So what you end up doing is you end up with a model that enables you to understand the stress in the rail, but it also allows you to understand how the load is distributed around the structure. So the two things, just to be clear, one was what is the additional capacity left in the track that we can rely on in our geometry with our track configuration, with fixings like lateral end plates or check rails, guardrails. What is our capacity? And then actually understanding what load will be generated, and therefore what stresses will be induced in the rail or in the substructures themselves. So this piece of work is probably worthy of a further PWI presentation in its own right, but and a lot of it goes back to first principles. So it had an independent review, both our Cat 3 checker, but also Brian Whitney at HQ helped us go through this, and we were able to demonstrate that that CWR can be put over the structure and the additional stresses in the rail can be kept within acceptable limits, and that the load from the traction and braking as it is applied to the rail, how it distributes into the structure. And with our nice new stiff West Coast box, we take away lots of load from the existing structures, and by doing so we remove the need for the strengthening. A bit of a model, but I'm running out of time, so I'm going to go quickly. Designed to impact on the railway environment. This is the ALO hoarding that's slotted in between the abutments and the track with that 3 meter limit that I mentioned earlier that defined our geometry. You go through quite a lot of pain to get it in, and you can see them installing some of the uprights there. But what it enables you to do is work adjacent to the line. I will show a little bit more of that in a minute. But also as part of designing to minimise the impact on the railway, what we did was to remove all the OLE support to the 10-foot so that we could slew the cables that existed running parallel with the works onto the ends of the sleepers effectively, and we didn't have to cut or sever any of the big telecoms cables or signalling cables running through the vicinity, which would have been a significant delay to the works and a risk to the programme. We also had two 25 kV feeder cables that we needed to slot down the sesses. So effectively, what we're doing here is we're protecting volumes or spaces, namely OLE support in the 10-foot. SES is used for cables of various types. We then have a segregation or separation using the ALO barriers, and then you can continue with all the civils activity outside that. So we keep everything in a safe and orderly way. As I was saying earlier, to make sure we could get a TSI compliant OLE arrangement, the OLE was designed in an integral manner with the structure. And you can see that we've got a couple of bays where we have to put in full sets of assembly, and we also need to attach stovepipes on quite a few of the intermediate beams, because we haven't got the catenary wire. So current delivery, we're on the final straight here, guys and girls. We commenced looking at this alternative in April 2019. We managed to get to a signed Form 1 and a formal agreement to change to a partial reconstruction in August. By June, we'd got a signed Form 2 and we'd started dismantling. The dismantling scheme, it isn't demolition, it's definitely dismantling. This is a 1,200-ton crane and was capable of lifting out decks, 300-ton decks up to 25 meters away, and it could lift half decks effectively at 40 meters. So a little bit different from the cranes you saw at the beginning for installing the structure. The decks themselves were broken free by these arrangements of jacks, whereby we effectively use the crossheads to push. It's like using a can opener, is my best description, to kind of free the deck. So when you're pulling it on the crane, you know it's clear and will come away. To make sure that locations where we were very tight, we use some of these underslung saws. And you can see on the right-hand side the patches plates, which are connected to those swan necks you saw to do the can opening, and enable us to put a beam over the top. And simple thing is you just lift it out. So this is some progress photos of when it was being removed at the back end of last year. You can see those can opening arrangements at each end, and you can see that the cranes on the right with some of the decks removed as the work progressed. Some nice arty photos of the decks coming out. Loaded onto SPMTs and moved to a site where they were recycled and used for material for the rest of the job. So by October, the structure had gone, and we commenced with the piling, pile caps, and pier construction. A few photos here. You can see a piling rig working behind one of our ALO hoardings there. That's on the east side. And the handrail you see to the left of the site is the extent of the network rail boundary. So you can see how tight we were in terms of footprint and why we couldn't, another reason why we couldn't expand wider on this side. On the west side, sorry, on the east side, I'll get right, on the west side, we were far less constrained, and we were able to use bigger pieces of piling kit, which could produce probably, I'm trying to think, I think they produced 6 piles for every one we got out of the rig on the other side. Here we have the piles in situ now, and they're dug down to prepare for the underside of the pile cap. You can see our barrier now on the left, holding up the West Coast Main Line. And you can see from the diagram on the right how that works. Another shot of the same sort of thing. That's a complete pile cap with the starter cages for the shell units. Shell units being put in over the top of the cores. Then we're installing the cages. I think I've shown you some of those earlier. And here we have, towards the end of April this year, a shot that shows the new piers complete. Some cores still to concrete and the sill unit still to put on, but substantially complete. You can see the OLE supported in the centre, in the 10-foot, and you can see the protective ALO hoardings wrapping around the piers. So May 21, just passed, we put in the beams for the span 18 over the West Coast Main Line, and here you have one of the beams on the hook, and about to swing around and drop it onto the West Coast, over the West Coast spans, or place it carefully, should I say. And here's an animation showing the site and how the works progressed, were undertaken, effectively making sure that the beams went in and the kit, or the OLE kit, was transferred to the structure in a sequential manner. Works occurred last weekend and were successfully completed, which was good news and a great relief to the project team who have been working virtually day and night to get to that last point over the last few months. And a couple of shots of final bits of clearing up and OLE being tidied up. Beams on top of the sills, shot from underneath the new structure. And you can see the cabling and cable route down to the left-hand side in front of our barrier. And we're looking to target completion of the structure so we can run our track renewal machine and the rest of the track infrastructure across the structure by November 21, so a few months left to go. So, closing summary. Enablers. What are the enablers to this? How can projects be, or what were the key enablers for this project? There is a real piece around the alignment of all the parties' interests and the alliance structure in promoting that and assisting it. The decision-making focus around the overall project delivery and risk mitigation, because it's all about risk management when you get into the detail here, whether it's the risk for the maintainer with the structure that we leave them with, or the risk to actually how you deliver the structure. The team we had, there's some exceptional individuals in there, and everybody played their part, from the client side to the asset owner, contractor to the designer, and it makes a huge difference to how things can be done when they need to be. The imperative of the alliance, if they didn't get this right, they didn't have a contract and they didn't have a viable scheme. And the use of digital delivery in a lot of the work we did, I haven't used much of it in my presentation, which you'll have to forgive me. But the digital delivery part enabled a much more progressive delivery and assurance, so that everybody could have confidence in what was going on and that all the bits would fit together as they should. What did the scheme actually provide at the end of the day? Well, it provided cost and program certainty to all the parties and risks that the parties could accept. It allowed us to deliver the flyover in circa 20 months from signing a Form 1 to putting the beams over the West Coast, which I think most would regard as being quite impressive for our industry. Although we lose an iconic structure and a very innovative piece of rail infrastructure, we replace it with something that is actually safe and maintainable and will provide good service to East West Rail Co. So it's a reasonable trade-off, although there are lots of bits about the original structure that I think were very innovative for their time, but some of the consequences were not fully understood. So lessons. Some of our structures out there are really complex with unobvious defects and failure modes, and you need to take your time to really understand them. Well, that's probably my next point, isn't it? Extensive investigation assessment. You've got to really understand the structure before you decide what you're doing to it. And some of the activity to kind of rush those early first stages and make decisions quickly, they need to be done in context and some of these structures will not yield their secrets quickly. And solutions that align stakeholder objectives can be delivered efficiently and quickly, even on the railways. Here, we had a solution that the RAM wanted, that the network was actually cheaper than the alternative on the books, so the overall client DFT stroke network rail client side were behind. It gave work that fitted the profile of Langs and Volkers. So you ended up with all these parties coalescing around the scheme and wanting to make it a success. So having that, getting those objectives aligned is really important. Right, thank you very much for listening to me. Hopefully that wasn't too long. I've got a nice picture of a sunset I can sail off into. But first, any questions?
That was great. I've got a combination of two questions which basically cover the same thing. The first part element is from Andy Savage. Richard, many thanks for the presentation. Most interesting to see the technical issues. Any idea why the original structure did not appear to have passenger platforms when Oxford-Cambridge was seen as a major route at the time the flyover was built? And then to go along with that, therefore, from Alistair Donaldson, there was an aspiration to have platforms on the WCML flyover portion to link to the lower station. Where is the interchange now?
Right. I don't know why the platforms were never put on in the first place. No idea on the history on that, so I'm very sorry, Andy. With respect to the new structure, that there is as part of the scheme, there is a new station coming in at Bletchley High Level, and that is just off the structure to the northern end. So as you get off span 37, that's effectively the end of the platforms as they sit at the moment. The structure, what we have done in future-proofing the railway, the platforms can continue out onto the structure. What we've done is an outline design that is independent of the structure itself. But effectively there's an outline design for that as well. So the scheme initially will deliver 4 car platforms just off the structure, and there's another 4 cars that can go onto the structure itself should they be necessary as demand grows.
Right, another question I have is from Paul Gray. A really interesting presentation. Are there many other structures like this in GB, or is this a one-off? To what extent did the original alignment line up with modern needs?
Right, I am not aware of another structure like this. I'm sure some of the features will exist in other structures though. So the fact that we're, as I've said, it's 4 different bridges, there may be aspects of all those bridges somewhere. So I think there are some lessons from each, how we've ended up dealing with each of them. And the second question was regarding modern needs. The alignment in terms of track geometry restricts it to 40 miles an hour, which isn't necessarily ideal, but isn't that bad either, especially if we're going to stop most of the east-west services at Bletchley High Level. But you could have chosen a slightly flatter curve at the, or if the geometry had been kinder, you could have had a flatter curve at the western end, because it's those spans that are very tight.
I've then got a question from John Fancoat. Will there be provision for installation of OLE on the EWR route at a later date?
Yes, we've as the scheme overall, there's a requirement to provide passive or not preclude OLE. We looked into how the OLE could be attached to this structure as part of the design, and it's relatively straightforward to post-fix onto the new elements as well as the existing structure. The OLE system doesn't impart significant loads in comparison with the rail supporting elements.
I then got a question from Nicholas Gibb. Were you asked to carry out a PAS 2080 carbon management in infrastructure assessment?
I'm sure there were certain environmental assessments required. I'm not aware of all the details and whether that specific obligation was undertaken. My colleagues back at East West Railco will be able to answer that, but a significant amount of work was done to minimise the environmental impact of the scheme as a whole, both ecologically and environmentally. The structure isn't the prettiest though, and the structure isn't the lightest, but that's forced more by the geometry of the site than anything else.
I've then got a number of thanks to give you before Ian. Andy Savage to everyone. Richard, an amazing, concise yet comprehensive presentation. Many thanks for giving it. I have really enjoyed it. Conrad Bassoon. Thank you, Richard, and the PWI for an interesting hot off the press presentation. Brian Whitney, your friend. Thanks, Richard. Great to see what were many reports and drawings a few years ago actually getting built. Fascinating to see the detail of the civils work. Andy's come back again. Rugby Flyover was pretty contemporaneous to Bletchley as part of the 1950s upgrade. It had its own problems. ASR, as I recall, when I became DCE, there was a lot of discussion about removing it, but it seems to have been restored. Peter Halliwell, very informative presentation. Thank you for the refurbished elements. By how much has their life been extended?
Right, on the refurbished parts, which are the kind of the northern and the southern spans, they have capacity for the main spans themselves of what's effectively full RU load, as I would have called it in old money. So it's RA15 effectively. So they have a lot of, they've got the strength in them is not an issue. The condition of them is not bad, and what we're doing is we are waterproofing them properly and creating proper drainage, which will stop the kind of degradation of them. So we're putting in quite a lot of preventative measures. To quantify how long that will provide any additional life is very difficult. You would expect a structure like this to last 120 years. It's done 60 already. Giving them a good overhaul now should help them see their following 60 years.
Okay, has anybody else got any other questions? Oh, an anecdote from Alistair Donaldson. My father was on the design team at the last minute before contracting being let. BR asked for OLE mast bases. They looked like an afterthought tacked on. They were.
They were, and we've removed a few of them, but yes, they were there, and we wouldn't be relying on them if we were to put electrification on.
I'd hand over to Ian now. Thank you very much.
Thanks, Kevin. Thanks, Richard. Yeah, really, as everybody said, a really informative and up-to-date presentation, really, and showing some real insight and knowledge into what's happened and how things have been completed. And it was great to see sort of technology at the end there and how it was all going to be built and timelined and everything. So yeah, amazing presentation. Thanks very much. Can I hand over to Paul Gray to do the vote of thanks, please?
Yeah, so as everyone said, thank you very much, Richard, for a really engaging presentation. It was great to see in the presentation a mix of old photos, clear diagrams and animations that really sort of told the story and bring it all to life. So yeah, really engaging presentation. There's quite a few things I've scribbled down as observations, but some of these have been covered in the questions. So just a few things I just wanted to sort of say to you, really. I thought it was great to see the assessment work of the bridge, or the various investigation work that you carried out to try to see what you could save and how to make better use of what was there. And it was really good that you're able to reuse some of the existing components, and with a view to, I guess, recognising cost savings and also carbon savings as well. So that was really good. Having sort of worked on the area for quite a number of years myself and driven under Bletchley, this bridge for many years, it was really good to see the detail and how it all worked and stayed up there. So that really was something that made it really come to life for me. The complexity of the structure was something that I could barely sort of note down the terms you use, but to use things like pre-informed, post-tensioned, and all the different mixes was really a tribute to the people of the day that built it, really, and were sort of perhaps really leading the way for engineers that for us that have followed. So really top presentation. And I think if my colleagues can get to the microphones as quite quickly, I think I'd just like my colleagues to join me in the vote of thanks and thank you in the usual way. Thank you, Richard.
Thank you very much.